For this example, it will be necessary to have a graphing calculator handy, so I'm going to recommend that you pause the video and grab a graphing calculator. I have mine ready to go. We are going to find the area under the curve y equals x squared between x equals 0 and x equals 1. Now for our calculations, we are going to use n equals 4. Now to give you an idea of what this is going to look like, we need the graph of y equals x squared. Looks like a parabola opening in the upward direction. We'll say that this point right here represents x equals 1, and here's x equals 0. So what we do is we break up our given interval from 0 to 1 into a total of n equals 4 subintervals. And we'll also bring in some heights so that we can see how tall these rectangles are going to be. I'd like to start this process by using a left-hand approximation. So use left endpoints. So I'm actually going to start on the right-hand side. For the last interval, the left endpoint would be this value right here, and if we connect this over to here, this is the area that we are going to be using to approximate the last interval. On the second to last interval, we connect left endpoint straight across to create a rectangle. For this interval, we connect across from the left. Now, when we connect across from the left on the first interval, we're actually connecting the point 0, 0 over there, so that height is going to be 0. So what I'm going to do is set up a little table of all the things that we're doing. So we have a total of 4 intervals. We should figure out the length of each of those intervals. Our delta x value is going to be equal to b minus a all over n. b minus a is referring to 1 minus 0, and n is referring to 4. So the length of each subinterval is going to be 1/4. So the first interval starts at 0 and will go up to 1/4. The second interval will start at 1/4 and go up to 2/4. 2/4 being equal to 1/2. Third interval will go from 2/4 to 3/4, and the last interval will go from 3/4 to 1. Now, we are using a left-hand approximation, so when I refer to x sub I star, the x value that we'll use to create these heights, we're going to be using the left endpoint. So 0 for the first one, 1/4 for the second one, 1/2 for the third one, and 3/4 for the fourth one. Then I'm going to take each of these values and I'm going to plug it into the given function, which in this case was y equals x squared. So we'll see 0 squared, which is 0. 1/4 squared, which is 1/16. 1/2 squared, which is 1/4. And 3/4 squared, which is 9/16. To turn these into areas, we'll need to multiply the height of each rectangle by the length of the base. Length of the base we calculated to be 1/4, so I'm going to take 1/4 times each of these heights. So 0 times 1/4 gives us 0. 1/16 times 1/4 gives us 1/64. 1/4 times 1/4 gives us 1/16. And 9/16 times 1/4 gives us 9/64. These 4 numbers that we just calculated represent the area of the leftmost rectangle, the rectangle right next to that, the rectangle right next to that, and then the rectangle in our rightmost column. If I add all of these up, this is going to give me an approximation of the total area. This is where the calculator is going to come in handy. We'll do 1 over 64 plus 1 over 16 plus 9 over 64. Math enter enter tells me that this is 7/32. or 0.21875. I can tell you right away, based off of the picture that we created, that this number underestimates the total area in there. I can tell that it underestimates because we have a whole bunch of blank spots where there is no area. So this is an underestimate. What I'd like to do is repeat this process, except instead of using a left-hand approximation, I'd like to use a right-hand approximation. So for the right-hand approximation, we will use right endpoints. So recopying our area that we're trying to find. Here's one. Split it into 4 intervals like so. And connecting heights like so. For right-hand endpoints, this time we'll be taking the right endpoint for each interval and connecting it over to the left endpoint for the interval, and repeating this process all the way down. So now the total area that we're going to be calculating will look like this. I can tell you right away that the area that we will calculate will be an overestimate of the actual area. Regardless, our 4 intervals, once again, will be the same as before. That'll be 0 to 1/4, 1/4 to 1/2, 1/2 to 3/4, and 3/4 to 1. Our representative point from each interval this time is going to be the right endpoint of each interval. You'll notice as I'm copying down the right endpoint of each interval, 3 of these are being reused from the previous example. The one that changes is the fact that we no longer have the left endpoint of 0, but we now do have the right endpoint of 1. I will be plugging these into the given function, which is, again, x squared. So squaring each of these values, we'll get 1/16. Squaring 1/2 gives us 1/4. Squaring 3/4 gives us 9/16. And squaring 1 gives us 1. We'll turn each of these y values into an area by multiplying by the base. So take each thing that I just calculated, 1/16, and multiply by the length of each interval. Length of each interval was 1/4. We said that on the previous example. So now it's on the previous page. So we multiply each of these by 1/4. We will get 1/64, 1/16, 9/64, and again, those should look familiar from the previous example. And finally, 1/4. If I add all of these together, I will get the total area that is an overestimate for what we're doing. Now you'll notice that I did that without the use of the calculator. I notice that the only thing different about the calculation is that to add, well, we already added these 3 numbers together from the previous example, then I just added this one on and got a common denominator. I've already mentioned this is an overestimate for the area. So based off of the underestimate, I know that the actual area is going to be between these 2 values. Oops, right and approximation. So the actual area is going to be somewhere in between. I can probably just use less than and greater, or less than rather than less than or equal to. But the actual area is going to be somewhere between these 2 values. Now with that in mind, if you want to get the best possible approximation for this, based off of the work that we've done, you can take the average of these 2. So if you take the average of these 2, grab that calculator one more time, that'll be 11/32, which is equal to 0.34375. Now, of the three calculations that we just did, this one is probably the best approximation that we did. Now, with that in mind, the book also says that there are better ways to approximate this area. So for the best possible approximation, the larger the value of n you use, the better your approximation is going to be. Now with that in mind, the book then went on to calculate several different values based off of different values of n. I'm going to recopy what we just did. We just did n equals 4. We got a left-hand approximation of 0.21875. A right-hand approximation of 0.46875, and an average of 0.34375. The book lets us know that if you use n equals 10 for this, which is a lot of calculations, you get a left-hand approximation of 0.285 and a right-hand approximation of 0.385. The average of these two numbers is 0.335. If you were to dial this up to n equals 30, which is a lot of calculating, you get a left-hand approximation of about 0.3169 and a right-hand approximation of about 0.3502. The average of these two values, well, I'm going to need my calculator for this one. 3502, divide that in 2. I'm getting about 0.3336. when rounded to the fourth decimal place. However, because we're in quarantine and don't have anything better to do, we could also bump this up to n equals 50 and perform those calculations. That would be 0.3234 for the left-hand approximation, 0.3434 for the right-hand approximation, and 0.3334 for the average of those two. Now, do keep in mind that one of the things that we talk about in Calc 1 is the concept of taking a limit, which is using data that you have in front of you to make an inference about an actual value of something. Now, the more we increase the value of n, the more I'm seeing the average get closer and closer to a particular quantity. And for that, I'm going to say, doesn't it look an awful lot like 1/3? 0.3333333333333333333, etc. I wonder how big n would have to be to basically make that happen. If you happen to see a limit as n approaches infinity in the next couple sections, don't be too shocked.